Chapter 8 Rate-Distortion Theory. In Chapter 4 and Chapter 5, we discussed source coding, where the message is decoded by the decoder perfectly or almost perfectly. In this chapter, we will discuss information transmission with distortion. Consider compressing an information source with entropy rate h at rate r strictly less than h. By the source coding theorem, Pe, the probability of decoding error, tends to 1 as n, the block length, tends to infinity. Under such a situation, information must be transmitted with distortion. The question is, what is the best possible trade-off? Specifically, we will introduce the single-letter distortion as a distortion measure between a source symbol and a reproduction symbol. We will also introduce the Rate-Distortion function Rd. With the Rate-Distortion theorem for an IID information source, the Rate-Distortion function Rd is seen to be the fundamental trade-off between the rate of the source code and the distortion incurred by the code. Section 8.1 Single-letter distortion measure. Let x sub k, k greater than or equal to 1, be an IID information source with generic random variable x with distribution px, where the alphabet x is assumed to be finite. Consider a source sequence bold x equals x1, x2 up to xn, and a reproduction sequence bold x hat equals x1 hat, x2 hat up to xn hat. The components of x hat take values in the reproduction alphabet x hat, which is also assumed to be finite. In general, the reproduction alphabet x hat may be different from the source alphabet x. For example, the reproduction sequence x hat can be a quantized version of the source sequence x. A single-letter distortion measure is a mapping D from x times x hat to r plus, where r plus denotes the non-negative real numbers. The value d x hat denotes the distortion incurred when a source symbol x is reproduced as x hat. For a source sequence x and a reproduction sequence x hat, the average distortion between x and x hat induced by a single-letter distortion measure d is defined by the average of the single-letter distortion measures. That is 1 over n times summation k equals 1 up to n d xk, xk hat, where d xk, xk hat is the distortion of the kth symbol in the sequence. We now give some simple examples of a distortion measure. Let the reproduction alphabet be the same as the source alphabet. The first distortion measure is called the square error, which is defined as follows. dx x hat is equal to x minus x hat square, where the alphabet x and the reproduction alphabet x hat are the real numbers. The second example is called the Hamming distortion, which is defined by dx x hat equals 0 if x is equal to x hat, that is, the reproduction is correct, and is equal to 1 if x is not equal to x hat. Here, the symbols in the source alphabet x do not carry any particular meaning. Let the random variable x hat be an estimate of the source variable x. If d is the square error distortion measure, then the expectation of the distortion between x and x hat is called the mean square error. If d is the Hamming distortion measure, then the expectation of the distortion between x and x hat is equal to probability x equals x hat, that is, the reproduction is correct, times 0, the corresponding distortion, plus the probability that x is not equal to x hat, that is, the reconstruction is incorrect, times 1, the corresponding distortion measure. And this is equal to the probability that x is not equal to x hat. That is, the expected distortion between x and x hat is the probability of error. This is so because the random variable dx hat is the indicator function for the error event. For a source sequence x and a reproduction sequence x hat, the average distortion dx hat gives the frequency of error in the sequence x hat. Now we talk about normalization of a distortion measure. For a distortion measure d, for each source symbol x, let x star hat of x, which is a reproduction symbol depending on the source symbol x, be the x hat that minimizes dx and x hat over all possible x hat. A distortion measure d is said to be normal if Cx, defined to be the distortion between x and x star hat of x, is equal to 0 for all source symbol x. That is, for a normal distortion measure, for every source symbol x, there exists a reproduction symbol x hat such that the distortion is equal to 0. In example 8.6, we let d be a distortion measure defined by the following table. In this table, the source symbols are 1 and 2, and the reproduction symbols are a, b, and c. Then x star hat of 1 is equal to a, because on the first row, the smallest distortion is equal to 2, which is under the column for the reproduction symbol a. Likewise, x star hat of 2 is equal to b, because in the second row, the smallest value is 3, which is under the column for the symbol b. A normal distortion measure is one which allows a source x to be reproduced with 0 distortion. As examples, the square error distortion measure and the Hamming distortion measure are normal distortion measures. If a distortion measure d is not normal, it can be normalized as a distortion measure d tilde, defined by d tilde between x and x hat is equal to d between x and x hat minus cx for all x and x hat. As we will see, for the establishment of the Rate-Distortion theorem, it suffices to consider normal distortion measures. Let d be a distortion measure defined in the last example. Here, C1 is equal to 2, and C2 is equal to 3. Then d tilde, the normalization of d, is given by the following table, which is obtained from the table for distortion measure d by subtracting the value 2 from the first row and subtracting the value 3 from the second row. Let x hat be any estimate of the source variable x which takes values in the alphabet x hat. Then the expectation of the distortion between x and x hat is equal to summation x hat px x hat times dx x hat. Now dx x hat can be written as d tilde x hat plus cx. Here we can write this into two double summations, where the first double summation is equal to the expectation of d tilde between x and x hat. For the second double summation, px hat can be written as px times px hat given x times cx. Now cx does not depend on x hat, so it can be taken outside the summation over all x hat, and summation x hat px hat given x is equal to 1. So this is equal to summation x px times cx. Upon defining delta equals summation x px times cx, we have expectation d x hat equals expectation d tilde x hat plus delta, where delta is a constant which depends only on px and d, but not on the conditional distribution px hat given x. In other words, for a different random variable x hat, the value of delta does not change. Let x star hat minimizes expected distortion between the source variable x and a constant estimate x hat over all x hat, and define d max to be the minimum of this expectation. Note that x star hat is not the same as x star hat of x, and x star hat, which is a constant reproduction symbol, depends on px. In other words, for different source distributions, we can have different x star hat. The idea is that if we know nothing about a source random variable x except for its distribution px, then x star hat is the best estimate of x, as it is the constant estimate that gives the minimum expected distortion. And d max is this minimum expected distortion between the source variable x and a constant estimate of x. The notation d max is a little confusing, because in fact it is the minimum expected distortion. Nevertheless, we are going to see very soon that this notation actually makes sense. Specifically, let both x star hat be the constant sequence taking values x star hat to be the reproduction sequence, then the distortion d max can be asymptotically achieved, because by the weak law of large numbers, the distortion between the random vector x and the constant reproduction sequence x star hat is equal to 1 over n times summation k equals 1 up to n. The distortion between the random variable x sub k and the constant symbol x star hat tends to the expectation of the distortion between the generic random variable x and the constant reproduction symbol x star hat, which by definition is equal to d max. This means that with a constant estimate alone, the distortion d max can be asymptotically achieved. Therefore, it is not meaningful to impose a constraint d greater than or equal to d max on the reproduction sequence. This is why we use the notation d max, because this is the maximum distortion we would ever care.